April 18th, 1955. Princeton Hospital. A cramped room on the second floor where the world's most famous mind lies dying. Albert Einstein, 76 years old, grey hair wild against the white pillow, feels the aneurysm in his abdomen pressing against his spine like a fist. The rupture happened 5 days ago. The surgeons say they can operate, maybe buy him a few more years. Einstein refuses. He speaks slowly, choosing each word with the same precision he once used to dismantle Newton's universe. I want to go when I want. It is tasteless to prolong life artificially. His voice is calm, not resignation, permission. He has spent 5 decades bending space and time with nothing but thought. Now he will bend death the same way, on his own terms. The night nurse checks his vital signs. Einstein speaks to her in German. She doesn't understand German. His last words are lost. Around 3 a.m. on April 18th, something inside him tears wider. The bleeding becomes catastrophic. His brain, the most studied organ that will ever exist, shuts down. By dawn, he is gone. Within hours, Thomas Harvey, the hospital pathologist, removes Einstein's brain without permission. He weighs it. 1,230 grams, slightly below average. He slices it into 240 pieces, preserving each section in colloidin. Harvey will keep these pieces in jars and cardboard boxes for the next 40 years, moving them from job to job, state to state, claiming he is looking for the source of genius in the tissue itself. He will find nothing. The secret was never in the matter. It was in the motion. 3 days before his death, Einstein was still working. Not on relativity, not on the theories that made him immortal. He was working on something else, the unified field theory, the equation that would finally explain everything: gravity, electromagnetism, the quantum world, all flowing from a single source. He had been chasing this ghost for 30 years. Every colleague told him it was impossible. Every year proved them right. He kept going anyway. The morning he collapsed, there were pages of calculations on his desk, incomplete, the problem unsolved. Some failures are more revealing than success, but I am getting ahead of the story. We need to go back before the fame, before the theories, before anyone called him genius. Back to when he was just a stubborn boy who couldn't keep his mouth shut in class, who failed entrance exams, who couldn't get a job. Back to the moment when being unwanted by everyone became the exact condition that let him change everything. Before we go there, though, I want to ask you something. If this story is pulling you in, if you want to see where it goes, do me a favor, hit the like button, subscribe to the channel. It genuinely helps, and I'm curious, where are you watching from? Are you in Berlin, Tokyo, São Paulo, New York? Drop a comment. I love knowing who's on this journey with me. All right, let's go back to the beginning. March 14th, 1879, Ulm, in the Kingdom of Württemberg, southern Germany. A city of narrow medieval streets and a cathedral spire that pierces the sky like a stone needle. Hermann Einstein and Pauline Koch have their first child. The baby's head is so large and misshapen that Pauline's mother gasps when she sees him. The doctors assure them the skull will normalize. It does. But something about that beginning, that entry into the world marked by strangeness, will follow the boy his entire life. His name is Albert. The family doesn't stay in Ulm long. When Albert is 1 year old, Hermann moves them to Munich. He and his brother Jakob are starting a company. Elektrotechnische Fabrik je Einstein and C. They manufacture dynamos, arc lamps, electrical measuring instruments. Munich in the 1880s is racing toward modernity, gaslights giving way to electric, horses giving way to trams. The Einstein brothers want to ride that wave. Hermann is an optimist. He believes in progress, in science, in Germany's future. The business will fail within 2 decades. But in 1880, everything seems possible. Albert grows up in a household that smells of machine oil and copper wire. The factory is nearby. Sometimes he visits, watches his Uncle Jakob test circuits, calibrate meters. The invisible force that makes the needles move fascinates him. Electricity flowing through wires you cannot see. Push a button here, light appears there. Cause and effect separated by mystery. This will be the pattern of his entire life. Looking for the hidden machinery behind the visible world, the workshop becomes young Albert's playground. He watches Jakob wind copper coils around iron cores, creating electromagnets that can lift metal objects as if by magic. The hum of the dynamos fills the air, a constant mechanical heartbeat. Workers move between benches cluttered with tools, wire spools, and half-assembled instruments. The smell is particular. Hot metal, insulation rubber, the sharp tang of solder. Albert stands in the corner, small hands behind his back, absolutely still, watching. Not fidgeting like other children, just observing. Jakob notices the boy's intensity. He begins explaining things, how alternating current differs from direct current, how resistance relates to heat, how a simple switch completes a circuit and allows electrons to flow. Albert listens without speaking, his dark eyes tracking Jakob's gestures. He doesn't ask many questions, but when he does, they're strange questions. "Uncle, where does the electricity go when you turn off the switch? Is it waiting somewhere?" Jakob laughs. The boy is only 6 years old and already thinking about conservation laws. One afternoon, Jakob gives Albert a broken compass to take apart. Albert carries it to the kitchen table and spends hours with it. Pauline finds him there at dusk, the compass disassembled into tiny pieces, each component arranged in careful rows. "Can you put it back together?" she asks. Albert looks up. His face is serious. "I want to understand why the needle knows where north is." She sits beside him. They work together in the fading light, reassembling the compass piece by piece. When they finish, Albert holds it up, watches the needle swing and settle. His mother sees something in his expression. Not satisfaction, deeper frustration. He has reassembled the device, but he still doesn't understand the invisible force. That will haunt him. His parents worry about him at first. He doesn't speak until he is 2. Even then, words come slowly. He has a habit of repeating sentences to himself under his breath, testing them before speaking aloud. The family maid calls him der Deperte, the dopey one. Pauline defends him. She sees something in the boy that others miss, an intensity, a stubbornness. When Albert is 5, she gives him violin lessons. He hates them. He will later say he hated everything about formal instruction at that age. But she persists. The violin, the discipline of music, will become one of the few things that calms him when his mind is racing. The violin teacher, Herr Schmid, is a stern man with a waxed mustache and no patience for children who don't practice. Albert refuses to practice. He sits through lessons with obvious contempt, holding the instrument incorrectly, dragging the bow across the strings to produce sounds that make Herr Schmid wince. After 6 months, the teacher tells Pauline that the boy has no musical aptitude whatsoever. She should save her money. Pauline ignores him. She continues the lessons with a different teacher, a younger woman named Frau Eckstein, who teaches differently. She doesn't drill scales. She plays Mozart, lets Albert hear the patterns, the mathematical relationships between notes. Something shifts. Albert begins to practice. Not because he's told to, but because he hears the structure underneath. Music, he realizes, is mathematics made audible. This changes everything. Also, when he is 5, his father shows him something, a pocket compass, a small brass disc with a glass face and a trembling needle inside. Hermann hands it to Albert during a fever, trying to distract the sick child. Albert stares at the needle. No matter how he turns the compass, the needle swings back to north, always north. Something invisible is reaching through space, through the brass, through everything, pulling that needle. The boy is mesmerized. Decades later, he will describe this moment as one of the two great wonders of his childhood. The other will be a geometry textbook. But the compass comes first. It plants a question. What forces are threading through the world unseen? He is not an easy child, not rebellious exactly, but allergic to authority. At age 9, he enters the Luitpold Gymnasium, Munich's most prestigious school. The German education system in the 1880s operates like a military academy transplanted to the classroom. Students stand when the teacher enters. They recite facts in unison. They do not ask why, only what. Teachers expect deference, obedience, memorization. Albert gives them none of these things. He questions everything. When a teacher explains that parallel lines never meet, Albert asks how we know. When told that the ether fills all space, he asks what the ether is made of. These are not the questions of a troublemaker. They are the questions of someone who cannot pretend to understand what he does not understand. The gymnasium is a grey stone building with high ceilings and narrow windows. Classrooms are arranged in rigid rows, 40 boys to a room, each desk bolted to the floor. The teachers wear dark suits and carry wooden pointers they occasionally slam on desks for emphasis. Instruction proceeds by rote. The teacher lectures. The students copy notes. At random intervals, a student is called to the front to recite what was just taught, verbatim. Any deviation is marked as failure. Any question is insolence. Albert's Greek teacher, Herr Degenhardt, is particularly harsh, a gaunt man with deep-set eyes and a perpetual scowl. He teaches ancient Greek through relentless memorization. Verb, conjugations, noun declensions. No discussion of literature or philosophy, just grammar hammered into young skulls through repetition and humiliation. Albert is terrible at it, not because he lacks intelligence, but because he cannot force himself to memorize patterns without understanding their purpose. Why does this verb decline this way? What is the logical structure? Herr Degenhardt does not entertain such questions. You memorize because I tell you to memorize. That is the only reason you need. One morning, Albert is called to the front to recite a passage of Xenophon. He has not memorized it. He stumbles through the first line, inventing words, guessing grammar. The class titters. Herr Degenhardt's face darkens. He walks slowly to where Albert stands, the wooden pointer tapping against his palm. You will never amount to anything, Einstein. You disrupt this class with your laziness and arrogance. Perhaps you should leave now and save us all the trouble. Albert meets his gaze, says nothing, returns to his seat. But the words land. They will stay with him for decades. You will never amount to anything. The teachers loathe him. His Greek professor tells him he will never amount to anything. Another says his presence disrupts the class. Albert is not stupid. His grades in mathematics and physics are extraordinary, but he is insolent. He makes teachers feel that their answers are insufficient. And they are. The model of education demands that students absorb doctrine without examination. Albert's mind operates by first principles. He needs to rebuild everything from the ground up. This incompatibility will define the next 2 decades of his life. At home, he discovers sanctuary. A family friend named Max Talmud, a medical student, begins visiting for dinner every Thursday. Jewish tradition, welcoming a poor student for a meal. Talmud is only 10 years older than Albert, Young enough to remember being curious, he brings the boy books. First, a geometry textbook. Albert reads it cover to cover in weeks, solving every problem. He is 12. Talmud brings him Kant's critique of pure reason. Too advanced, surely, for a child. Albert reads it anyway. He doesn't understand all of it, but he understands enough. The idea that space and time might not be absolute features of reality, that they might be structures of human perception, lodges in his mind like a seed. Thursday dinners become the center of Albert's week. Pauline prepares simple meals, soup and bread, sometimes chicken. The family sits around the table, Hermann at the head, Pauline to his right, Albert and his younger sister Maya on the other side, and Max Talmud next to Albert. The conversation is lively, ranging across politics, religion, science. Talmud asks Albert what he's reading. Albert describes the geometry problems, his voice animated in a way it never is at school. He talks about Pythagoras, about the strange fact that you can prove the theorem without measuring anything, just using pure logic. Talmud nods, encourages him. Have you thought about where geometry comes from? Whether the axioms are true because they describe reality, or whether reality conforms to the axioms we choose? Albert stares at him. This question has never occurred to him. Are there other geometries? Talmud smiles. There are. Non-Euclidean geometries where parallel lines do meet, where the angles of a triangle don't add to 180 degrees. Albert's mind reels. The idea that mathematics can contain multiple self-consistent systems, each based on different axioms, is intoxicating. Later, much later, he will use non-Euclidean geometry to describe the curvature of space-time. But at 12, he just feels the ground shifting under his feet. If geometry is a choice, what else is? Talmud sees what the teachers don't. This boy is not deficient. He is operating at a different altitude. The questions that annoy his professors are the questions that drive science forward. Talmud encourages him, keeps bringing books, physics, philosophy, mathematics. Albert devours them all. By age 14, he has taught himself calculus. He reads Newton's Principia. He reads Maxwell's equations describing electromagnetism. He is encountering the fundamental laws of the universe in his bedroom while his teachers drone about Latin declensions. But the world does not care what you know if you do not have the right credentials. And Albert, at 15, is about to make a decision that will nearly destroy his future. His family's electrical company is failing. Hermann has borrowed money, expanded too quickly, lost contracts. In 1894, the Einstein brothers closed the Munich factory and moved the business to Italy, hoping for better luck. The family relocates to Milan. Albert is left behind at the gymnasium to finish his diploma. He is miserable. The school is a prison. His family is gone. He is alone in Munich, boarding with a distant relative, dragging himself to classes where he is openly despised. The boarding house is a narrow building on a side street run by a distant cousin of Pauline's, a widow named Frau Meyer. She is not unkind, but she is overwhelmed, taking in boarders to make ends meet. Albert shares a room with two other boys, both older, both gymnasium students. The room is barely large enough for 3 beds and a single desk. The walls are thin. At night, Albert can hear Frau Meyer coughing in the next room, the sound wet and painful. The food is adequate but repetitive: potatoes, cabbage, dark bread. Once a week, a thin soup with bits of meat. Albert writes letters to his parents every Sunday. Short letters, careful not to worry them. He describes his classes in neutral terms, mentions the weather, asks about Maya. He does not mention how much he hates the gymnasium, how the teachers single him out, how he lies awake at night, staring at the ceiling, feeling the walls press in. His parents have enough to worry about. The business is failing. They are starting over in a new country. He will not add to their burden. But by December, he cannot bear it any longer. He walks to a doctor's office, a physician he has never met, and requests a letter. He needs documentation of nervous exhaustion, a medical excuse to leave school. The doctor, an older man with kind eyes, examines Albert. "Are you sleeping?" Albert says no. "Are you eating?" Albert says, "When I can." The doctor writes the letter. He does not ask too many questions. He has seen this before, young men ground down by institutions that do not fit them. The letter is brief and clinical. The patient is suffering from nervous exhaustion and requires an extended period of rest away from academic pressures. He lasts 6 months. In December 1894, without consulting his parents, Albert walks out of the Luitpold Gymnasium. No diploma, no qualifications, just a letter from the family doctor claiming nervous exhaustion. He crosses the Alps on foot, shows up at his parents' door in Milan, and announces he is done with Germany. He is 16 years old and he has just committed educational suicide. Hermann is furious. Pauline is distraught. Their son has thrown away his future. In Germany, in the 1890s, a gymnasium diploma is the gateway to university, to a profession, to respectability. Without it, you are nothing. Albert doesn't care. He tells them he will study on his own, take an entrance exam to a university somewhere else. He promises he will make it work. His parents do not believe him, but they let him stay. Maybe the Italian sun will cure whatever madness has taken hold. For a year, Albert lives in Milan and Pavia with his family, technically doing nothing. No school, no job. He helps his uncle Jacob with electrical designs occasionally. Mostly, he reads physics, mathematics, philosophy. He takes long walks through the Italian countryside, thinking. There is a freedom in this year that he will never have again. No teachers correcting him, no schedule, just his mind and the problems he chooses to pursue. Later, some will call this year a waste, but it is the opposite. It is the year he learns that he can think without permission. The Italian light is different. Softer, warmer than Munich's grey winter skies. Albert walks for hours through olive groves and along dusty roads, a notebook in his pocket, pausing occasionally to scribble equations or diagrams. He is thinking about light, about electromagnetism, about the strange results of the Michelson-Morley experiment that failed to detect the ether wind. The experiment was conducted in 1887 when Albert was 8 years old, but he reads about it now in Italian libraries. The implications gnaw at him. If there is no ether, what is light moving through? He writes letters to his sister Maya, who is still in Milan with the family. She is 11, bright and curious. Albert explains physics to her in simple terms, testing his understanding by teaching. If light is a wave, it needs a medium to wave in. Sound is a wave in air. Water waves are waves in water. But light travels through vacuum. If there is no ether, how does that work? Maya writes back with questions of her own. Could light be something different from other waves? Albert considers this. Could it? The answer, years later, will be yes. Light is different. But in 1895, he is just asking. In 1895, he decides to apply to the Swiss Federal Polytechnic in Zurich. The Polytechnic is one of the best technical schools in Europe. It has an unusual admissions policy. You don't need a gymnasium diploma if you can pass the entrance examination. Albert is 16, 2 years younger than the typical applicant. He takes the test in October. He passes the mathematics and physics sections brilliantly. He fails everything else: French, chemistry, biology, literature. The failures are catastrophic. No diploma, no entrance, no university. The director of the Polytechnic, Albin Herzog, sees Albert's mathematics scores. He writes a note suggesting the boy finish his secondary education and reapply. He recommends the cantonal school in Aarau, a small Swiss town. Less rigid than German schools, Herzog says, the boy might do better there. Hermann and Pauline, desperate, agree. Albert enrolls in Aarau in late 1895. He is 17. He boards with the family of Jost Winterler, a teacher at the school. And something shifts. Aarau is different. The teachers encourage questions instead of punishing them. The pedagogy emphasizes understanding over memorization. Albert thrives. His grades improve. More than that, he feels something he has never felt in a classroom. Belonging. He hikes with classmates. He argues about science at the dinner table with Winterler. He falls in love with Winterler's daughter, Marie, his first romance. For a year, he experiences what education could be, freedom structured by curiosity. The Winterler house sits on a hill overlooking the town, a modest two-story building with a garden that smells of herbs and roses in the summer. Jost Winterler is a history teacher, but his real passion is philosophy. He believes education should cultivate independent thought, not obedience. At dinner, he asks his students questions without predetermined answers. What is justice? What makes a government legitimate? Can you ever know anything with absolute certainty? The conversations are vigorous, sometimes argumentative. Everyone talks over each other, laughs, challenges. Albert, who has spent years silent in classrooms, comes alive. Marie Winterler is 18, a year older than Albert. She has dark hair, a quick smile, and a love of poetry. She sees Albert not as the arrogant troublemaker his teachers described, but as someone intense and searching. They take walks together in the evenings, following trails that wind through the hills above Aarau. They talk about everything. She tells him about Goethe, about romantic ideas of nature and the sublime. He tells her about Maxwell's equations, about the mystery of light. She listens, really listens in a way no one has before they hold hands. He writes her poems, terrible poems that she treasures anyway. It is innocent, sweet, doomed. He also begins the thought experiments that will define his career. One afternoon, probably in 1896, he imagines himself riding alongside a beam of light. If you are moving at the speed of light, what does light look like beside you? According to Maxwell's equations, light is an oscillating electromagnetic wave, constantly moving. But if you are moving at the same speed as the wave, it should appear frozen, stationary. Yet Maxwell's equations say light always moves at the same speed regardless of the observer. A contradiction. This paradox will gnaw at him for the next 9 years. The solution will be special relativity. But in 1896 he is just a teenager wondering what light looks like when you catch up to it. In 1896 Albert does something else that will shape his future. He renounces his German citizenship. Officially, he claims it is to avoid military service. But the truth is deeper. He despises the authoritarianism of the German state, the militarism, the rigid hierarchies. He wants no part of it. For the next 5 years, he is stateless, a man without a country, without papers, technically illegal in most places he goes. It is both a practical nightmare and a kind of philosophical statement. He does not need a government's permission to exist. Later, he will become Swiss, later still American. But he will always carry this idea that nationality is an accident, not an identity. The universe does not care what flag you salute. In October 1896, Albert takes the entrance exam to the Polytechnic again. This time he passes. He enrolls as a student in the mathematics and physics teaching program. He is 18. He believes the hardest part is behind him. He is catastrophically wrong. The Swiss Federal Polytechnic is rigorous. The professors are brilliant. Albert's classmates are serious, disciplined, ambitious. Albert is none of these things. He skips lectures constantly. He reads what interests him instead of what is assigned. He spends hours at cafes discussing philosophy with friends instead of attending labs. His professors notice. more than notice. They are offended. One professor, Heinrich Friedrich Weber, initially admires Albert's mathematical gifts, but Weber teaches experimental physics using traditional methods. Albert finds the curriculum outdated. He says so, out loud. To Weber's face, the relationship sours. By Albert's fourth year, Weber despises him. Weber is a formidable figure. Tall, bearded, with a reputation for precision and rigor. His lectures are famous for their clarity. He demonstrates electromagnetic phenomena with elaborate equipment, shows students how to make exact measurements, emphasizes the importance of experimental confirmation. Albert attends the first few lectures, then stops coming. When Weber asks why, Albert says with characteristic bluntness that the course ignores modern developments. Maxwell's equations are barely mentioned. There is no discussion of Hertz's experiments confirming electromagnetic waves. The curriculum, Albert says, is 20 years out of date. Weber's face goes rigid. You think you know better than the curriculum? Albert shrugs. I think the curriculum should reflect current research. Weber's voice drops to a cold whisper. Then perhaps you should design your own curriculum, Herr Einstein, and perhaps you will discover that teaching requires more than arrogance. Albert does not back down. He stops attending Weber's lectures entirely, instead reading Maxwell, Hertz, and Boltzmann on his own. He will graduate, barely, but Weber will ensure that no academic position is offered to him afterward. The punishment for insolence is exile. But there is one person at the Polytechnic who sees Albert clearly. Mileva Maric. She is the only woman in the mathematics and physics program, 4 years older than Albert, Serbian, from a family in the Austro-Hungarian Empire. She is shy, walks with a limp from childhood tuberculosis, and is as obsessed with physics as Albert is. They meet in 1896. By 1898, they are inseparable, intellectually first, then romantically. They call each other Dolly and Johnny in letters. They talk about Hertz's experiments, Boltzmann's statistical mechanics, the nature of the ether. Mileva understands him. More than that, she challenges him. Some historians will later argue she contributed significantly to his early work. Others will dismiss this as myth. The truth is murky. The letters say our work, our research. But the published papers list only his name. What is certain is that Mileva is his first true intellectual partner. And that partnership will cost her almost everything. They meet in Weber's lecture hall, ironically. Mileva sits in the front row taking meticulous notes. Albert sits in the back, reading a book, occasionally glancing up when something interesting is said. After class, Mileva approaches him. "You're reading Helmholtz." Albert looks up, startled. "Yes." She sits down beside him. "What do you think of his theory of vortices?" They talk for an hour. She is the first woman he has met who speaks the language of physics fluently. She does not defer to him or pretend ignorance to flatter his ego. She argues with him, points out errors in his reasoning, suggests alternative approaches. He is fascinated. They begin studying together, long afternoons in the library, working through problems, debating interpretations. Their relationship shifts from intellectual to romantic so gradually that neither can say exactly when it happens. One evening, walking back from the library, Albert takes her hand. She does not pull away. They stop, and he kisses her, clumsy and earnest. She kisses him back. Later, she will write to a friend that she feels, for the first time, that someone understands her completely. He writes to her, when they are apart, letters full of physics and longing intertwined. "I am so lucky to have found you, a creature who is my equal in every respect." In 1900, Albert graduates from the Polytechnic. Barely, he is 4th out of 5 students in his cohort. Mileva fails her final exams. She will retake them and fail again. They plan to marry. Albert's mother, Pauline, forbids it. Mileva is too old, too foreign, too damaged. Pauline calls her a curse. Albert ignores his mother, but he has a more immediate problem. He needs a job. In 1900, if you graduated from the Polytechnic, you typically became an assistant to one of your professors. The professor mentored you, helped you publish, guided you toward an academic career. This was the pathway to becoming a professor yourself. Albert applies to every professor he studied under. Every single one rejects him. His grades are mediocre. His attendance was abysmal. Worse, his attitude. The professors remember his arrogance, his dismissiveness of their methods. One by one, doors close. He applies to universities across Europe for any position. Assistant, tutor, anything. Rejection after rejection. His classmates all find positions. Albert is left with nothing. The rejections arrive by mail, one after another, polite, curt, sometimes not even polite. We regret to inform you, the position has been filled. Your qualifications do not meet our current needs. Albert keeps them in a drawer, a growing stack of failures. He writes to his friend Marcel Grossman, trying to sound casual. Do you know of any positions? I'm exploring options. Grossman hears the desperation underneath. He writes back immediately. Let me ask around. This is the wound, the central trauma. Not a single dramatic event, but a slow accumulation of exclusion. The institutions of science, the academies and universities that are supposed to recognize talent, look at Albert Einstein and see only a troublemaker with poor marks. They do not see genius. They see a liability, and they shut him out. For 4 years, from 1900 to 1904, Albert scrambles for work. He takes temporary tutoring jobs, each lasting a few months before he is let go. He is living in poverty, borrowing money from friends, sleeping on their couches. Mileva is back in Serbia. They write letters constantly, but Albert cannot support himself, let alone a wife. The tutoring jobs are humiliating. He teaches mathematics to high school students whose parents can afford private instruction. The students are often uninterested, attending only because their parents insist. Albert tries to make the material engaging, to show them the beauty in equations, the elegance of proofs. Most don't care. They want to pass their exams and move on. One family fires him after 3 weeks. Their son, they say, finds Albert's teaching methods confusing. Too much theory, not enough drills. Another family keeps him for 2 months, then lets him go without explanation. The father pays him for the final week and suggests politely that Albert might be better suited for a different profession. Between jobs, Albert stays with friends. Michel Besso, an engineer he met at the Polytechnic, lets him sleep on a couch for weeks at a time. They talk late into the night. Albert describing his ideas about light and time, Besso listening patiently, asking questions. Besso will later say that Albert during these years had a kind of desperate energy, as if he knew time was running out, as if he had to solve these problems before the world crushed him entirely. Albert writes to Mileva almost daily. The letters are tender and anguished. He tells her he dreams of a life together, a small house, enough money to live simply. He tells her he is working on a paper about molecular forces. He does not tell her he is afraid that he will never escape this trap, that his mind, which he knows is extraordinary, will be wasted because no one will give him a chance. In 1901, he becomes a Swiss citizen. The process takes a year and costs him money he doesn't have, but he does it. Switzerland is neutral, democratic, functional. He likes the Swiss. They leave you alone. That same year, he publishes his first scientific paper, a study of capillary action in liquids. It is competent but unremarkable. No one notices. He sends it to his former professor Weber, hoping for encouragement. Weber doesn't respond. The rejections keep coming. In 1901, Albert applies to be a high school teacher. Rejected. He applies to insurance companies, thinking maybe he can use his mathematics elsewhere. Rejected. He writes to his friend Marcel Grossman, who was the top student in their polytechnic class. Grossman has a job, connections. Can he help? Grossman tries. He mentions Albert's situation to his father. Grossman's father knows someone at the Swiss patent office in Bern. They need a technical expert to evaluate patent applications. No advanced degree required, just a good understanding of physics and engineering. Grossman's father writes a recommendation. Albert applies. In June 1902, Albert Einstein becomes technical expert third class at the Swiss patent office in Bern. Salary 3,500 francs per year. Enough to live. The position is utterly beneath his education. His classmates are assistant professors at universities. He is a clerk stamping paperwork, but he takes it. What choice does he have? And something else happens in 1902. Mileva becomes pregnant. They are not married. In 1902, this is a catastrophe. An unwed pregnancy ruins a woman's reputation permanently. Mileva returns to her family in Serbia to hide the pregnancy. Albert stays in Bern, working at the patent office. In January 1903, Mileva gives birth to a daughter. They name her Liesel. Albert has never seen her. He does not travel to Serbia for the birth. He sends Mileva letters asking about the child's health, whether she looks like him. Mileva writes back, tense, worried. What will they do with the child? They cannot bring her to Switzerland unmarried. Albert's family forbids the marriage. They cannot support a baby on his salary. Liesel vanishes. Sometime in 1903 or early 1904, the child either dies of scarlet fever or is given up for adoption. No records survive. Albert will never meet his daughter. He will never speak of her publicly. When Mileva's letters mentioning Liesel are discovered in 1986, decades after both are dead, the world learns that Einstein had a daughter he abandoned. There is no way to soften this. He walked away. Whether the child died or was adopted, he walked away. Mileva never forgives herself. Albert compartmentalizes. This is the cost of survival. You bury what you cannot fix and keep moving. In January 1903, Albert and Mileva marry quietly in Bern. No family attends, just two friends as witnesses. Mileva moves into Albert's small apartment. She cooks, cleans, tries to restart her studies. Albert works at the patent office 6 days a week, 8 hours a day. Evenings and Sundays, he does physics, real physics, not the mundane calculations of his day job, though those aren't entirely wasted. The patent applications teach him to think about physical mechanisms, to visualize how devices work in three-dimensional space. But after work, he returns to the problems that obsess him. The nature of light, the relativity of motion, the strange behavior of molecules. The patent office is a utilitarian building in the center of Bern, 4 stories of grey stone with narrow windows. Albert's desk is on the 3rd floor in a large room he shares with 3 other examiners. The work is repetitive but not mindless. Inventors submit applications for electrical devices, mechanical gadgets, dynamos, clocks. Albert's job is to evaluate whether the claimed invention is genuinely novel and whether it would work as described. He reads each application carefully, visualizes the mechanism, identifies flaws or redundancies. Many applications are rejected. Some inventors resubmit with modifications. A few are genuinely clever. Albert enjoys the work more than he expected. It requires precise thinking, but it does not consume him. He finishes most applications quickly, leaving hours each day for his own thoughts. His supervisor, Friedrich Haller, is a gruff but fair man who notices that Albert completes his work efficiently. Haller does not mind if Albert uses spare time to scribble equations on scrap paper, as long as the applications are processed correctly. Albert fills notebooks during stolen minutes, working on problems that have nothing to do with patents. What would happen if the speed of light is constant for all observers? how would time behave differently in different reference frames? He calculates, crosses out, recalculates. He forms a study group with two friends, Konrad Habicht and Maurice Solovine. They call themselves the Olympia Academy, a joke name for three nobodies reading Hume and Spinoza in a cramped apartment. They discuss philosophy, epistemology, the limits of knowledge. These conversations matter more than Albert's professional isolation might suggest. He is learning to think about what can be known versus what must be assumed. Later, this will become the foundation of relativity. You cannot measure absolute space or absolute time. You can only measure relative motion. If you cannot measure something even in principle, does it exist? The Olympia Academy debates this while eating sausages and drinking cheap wine. The Academy meets weekly, usually at Albert's apartment. Mileva sometimes joins, sitting quietly in the corner, listening. The conversations range across science. Philosophy, politics. Habicht, an aspiring mathematician, brings questions about geometry. Solovine, a philosophy student, brings questions about empiricism. Albert brings questions about physics. They read Mach's Science of Mechanics, which argues that concepts like absolute space and absolute time are metaphysical baggage, not scientific necessities. Albert is electrified. Mach is saying what Albert has been groping toward. You should only include in your theories what can be observed. Everything else is speculation. One evening, Solovine asks Albert what he's working on. Albert hesitates, then begins explaining. If you accept that the speed of light is constant, and you accept that the laws of physics are the same for all observers moving at constant velocity, you run into a contradiction. Two events that one observer sees as simultaneous might not be simultaneous for another observer. Habicht interrupts. That sounds absurd. Albert smiles. It does, doesn't it? But I think it's true. He walks them through the logic, step by step, drawing diagrams on scrap paper. Solovine's eyes widen. If you're right, this changes everything. Albert nods. I know. But I need to work out the mathematics. In 1904, Mileva gives birth to a son, Hans Albert. This one they keep. Albert is 25 years old. He has a wife, a child, a steady job, and absolutely no recognition as a physicist. He has published 3 papers, all minor. No university has offered him a position. No established scientist knows his name. He is nobody. And in 1 year, he will change everything. The year is 1905. Later, physicists will call it the Annus Mirabilis, the miracle year. Between March and September, Albert Einstein publishes 4 papers in the journal Annalen der Physik. Any one of these papers would be career-defining. Together, they dismantle and rebuild the foundations of physics, and he does it while working full-time at the patent office. The first paper appears in March on a heuristic point of view concerning the production and transformation of light. Albert is addressing a problem that has plagued physics for years. When you shine light on a metal surface, it sometimes ejects electrons. This is called the photoelectric effect. Classical wave theory says the energy of the light should depend on its intensity, how bright it is. But experiments show something else. The energy depends on the frequency, the color. Bright red light does nothing. Dim ultraviolet light ejects electrons immediately. Why? Albert proposes something radical. What if light is not a continuous wave but a stream of discrete particles, quanta? Each quantum carries energy proportional to its frequency. When a quantum hits an electron, it transfers energy instantly. If the quantum's energy is high enough, determined by frequency, the electron escapes. If not, nothing happens. Intensity is irrelevant. This explains the experiments perfectly, but it also implies something deeply strange. Light, which Maxwell proved was a wave, is also a particle. Both, simultaneously. Classical physics cannot accommodate this. Albert doesn't care. The math works, the experiments confirm it. That is enough. He writes the paper in February, late at night. after Hans Albert is asleep. Mileva sits at the kitchen table, mending clothes, occasionally looking up to watch him. His handwriting is cramped, rapid, crossing out errors, adding corrections in the margins. When he finishes, he reads it aloud to her. She listens, nods. It's good. He seals it in an envelope and mails it to the Annalen der Physik the next morning. He has no idea if they will publish it. He does not have an academic position which makes him an outsider, but the editor, Paul Drude, publishes work based on merit, not credentials. The paper is accepted in April, published in May. This paper will win him the Nobel Prize 16 years later. But in 1905, most physicists ignore it. The idea is too strange, too radical. Light as particles, we settled this a century ago. Light is a wave. Everyone knows this. Albert moves on. The second paper appears in May, on the motion of small particles, suspended in a stationary liquid, as required by the molecular kinetic theory of heat. A title only a physicist could love. The paper addresses Brownian motion, the jittery, random movement of microscopic particles suspended in fluid. Observed by botanist Robert Brown in 1827, never explained. Albert shows that Brownian motion is caused by invisible molecules of the liquid colliding with the particle. Random thermal motion on the molecular scale creates visible motion on the observable scale. More than explain the phenomenon, Albert provides mathematical predictions: the average distance a particle moves in a given time, the relationship to temperature and particle size. Everything testable. Within a few years, experiments confirm his predictions exactly. The paper does more than explain Brownian motion. It proves atoms exist. This may sound strange. In 1905, many physicists still doubt atoms are real. You cannot see them. You can only infer them from indirect evidence. Some scientists consider atoms a useful fiction, a mathematical convenience. Albert's paper shows that atomic theory makes specific, testable predictions about observable phenomena. When those predictions are confirmed, atoms transition from hypothesis to fact. He has settled one of the great debates of 19th century science with a 20-page paper written in his spare time. He writes this paper in March between patent applications. The mathematics is straightforward but tedious. He calculates the diffusion of particles, relates it to viscosity and temperature, derives expressions for observable quantities. It is not glamorous work, but it is solid. He knows this paper will be taken seriously because it makes concrete predictions. If the experiments match, the theory is confirmed. If they don't, the theory is wrong. That is how science should work. Clear predictions, empirical tests. No ambiguity. The third paper appears in June, on the electrodynamics of moving bodies. No equations in the title. Dry, technical language. And it contains special relativity. The complete dismantling of Newtonian space and time. The idea Albert has been chasing since he was 16, imagining himself riding alongside a light beam. The paper begins with the principle of relativity, borrowed from Galileo and Newton. The laws of physics are the same in all inertial reference frames, all perspectives moving at constant velocity relative to each other. You cannot tell if you are moving or stationary by doing experiments inside a closed box. Motion is relative. Albert adds a second principle. The speed of light in vacuum is the same for all observers, regardless of their motion. This comes from Maxwell's equations, which imply light always travels at the same speed. But combining these two principles creates a paradox. If you are on a train moving at half the speed of light and you shine a flashlight forward, how fast is the light moving? Classically, you add the speeds. Half the speed of light plus the speed of light equals 1.5 times the speed of light. But Maxwell says light always moves at the speed of light. Only the speed of light, not faster, not slower. How can both be true? Albert realizes the only way to resolve this is to abandon absolute space and absolute time. Time and space must be relative, flexible, observer-dependent. If two events are simultaneous for one observer, they may not be simultaneous for another observer moving at a different velocity. Time itself flows at different rates, depending on motion. Space contracts in the direction of motion. These are not approximations or tricks. They are fundamental features of reality. The universe does not have a universal clock. Every observer has their own time, and all of them are equally valid. The mathematics is elegant, the conclusions are bizarre. Time dilation, length contraction, the relativity of simultaneity. Albert works through the implications systematically. He shows how Newtonian mechanics is an approximation, valid only when velocities are much slower than light. At high speeds, Newton's equations break. You need Einstein's. The paper is 23 pages long. It contains one citation to a friend. No references to prior work. No acknowledgement of debate. Just Albert, alone in his apartment, rewriting the rules of the universe. He writes this paper in May in a white heat of concentration. Mileva tells friends later that Albert barely ate or slept for weeks. He worked every spare moment, scribbling equations, staring into space, muttering to himself. She worries he is making himself sick, but she also sees that he is exhilarated. This is what he was meant to do. When he finishes the draft, he reads it to her, pacing the room, gesturing. She asks questions. What does it mean for time to slow down? He tries to explain. Imagine two clocks, one stationary, one moving. From the perspective of the stationary clock, the moving clock ticks more slowly. Both perspectives are valid. There is no absolute time. She frowns. But which clock is really slower? Albert shakes his head. That's the point. There is no really. It depends on your reference frame. In September, he publishes a brief follow-up paper. Does the inertia of a body depend upon its energy content? 3 pages. One of the most famous equations ever written appears on the second page, not yet in the famous form. Albert writes it as m equals E over c squared. Mass equals energy divided by the speed of light squared. Rearrange it and you get E equals mc squared. Energy equals mass times the speed of light squared. Matter and energy are interchangeable. A tiny amount of matter multiplied by the enormous speed of light squared contains a staggering amount of energy. This is the equation that will make atomic bombs possible. In 1905, it is a theoretical curiosity. No one knows how to unlock that energy. But the principle is there, waiting. 4 papers, photoelectric effect, Brownian motion, special relativity, mass-energy equivalence, written in 6 months in the margins of a full-time job in a city where no one knows who he is. And the world barely notices. A few physicists read the papers and think they are interesting. Some write to Albert asking questions. Max Planck, one of the most respected physicists in Germany, starts corresponding with him. But there are no job offers, no invitations to conferences, no acclaim. Albert is still technical expert third class at the Swiss Patent Office. The miracle year changes physics. It does not change his life. Not yet. Over the next few years, slowly, the scientific community realizes what has happened. Experimental confirmations start appearing. Other physicists begin citing his work. In 1908, Hermann Minkowski, one of Albert's former professors at the Polytechnic, reformulates special relativity using 4-dimensional spacetime geometry. Minkowski presents it as a unified structure, 3 dimensions of space plus 1 of time, woven together. Albert initially dismisses Minkowski's approach as unnecessary mathematical abstraction. Later, he will realize Minkowski gave him the tool he needs for the next leap. Minkowski presents his work at a conference in Cologne. Albert does not attend. He reads the published paper months later. His initial reaction, dismissive. Unnecessary complication, he tells Mileva. The physics is clear without all this geometric formalism, but as he studies Minkowski's equations, he begins to see the power of the approach. Space-time as a unified four-dimensional manifold, world lines tracing the paths of particles through this manifold. The mathematics is beautiful, and it makes certain calculations far simpler. Years later, when Albert is working on general relativity, he will return to Minkowski's framework. It will become indispensable. He will wish he had paid closer attention in 1908. In 1909, the University of Zurich offers Albert a position as associate professor. He is 30 years old. He quits the patent office after 7 years. Finally, he has an academic job. The salary is less than the patent office, but it comes with status. With access to students and collaborators, he begins lecturing, mentoring. He's not a natural teacher. His lectures are disorganized, full of tangents, but the students who pay attention see something. This man is thinking out loud, wrestling with problems in real time. It is messy and exhilarating. The lecture hall at the University of Zurich is a steep amphitheatre with rows of wooden benches and a large blackboard at the front. Albert's first lecture is on thermodynamics. He arrives late, slightly out of breath, carrying a stack of papers that he sets on the lectern without looking at them. He writes the first law of thermodynamics on the board, then pauses. Actually, he says, let me start somewhere else. He erases the equation and begins talking about heat engines, about Carnot cycles, about the strange fact that entropy always increases. He draws diagrams, erases them, redraws them differently. Some students are confused, others are riveted. This is not a polished performance. This is someone showing you how he thinks. After class, a student approaches. Professor, you didn't cover the material in the syllabus. Albert looks surprised. Oh, sorry, I'll cover it next time. But next time he does the same thing, following his own train of thought rather than the curriculum. The department chair receives complaints. Some students want a more structured approach, but others say it is the best class they have ever taken. Albert is unrepentant. If they want structure, they can read the textbook. I'm here to show them how to think. In 1910, Mileva gives birth to their second son, Eduard. The family is growing. Albert's reputation is growing, but cracks are forming. Mileva wanted to be a physicist. Instead, she is a housewife, raising children, managing the household, while Albert travels to conferences and collaborates with colleagues. She is brilliant and isolated. Albert is sympathetic in theory, but absent in practice. He works constantly. Physics is not a job for him. It is an obsession. Everything else, family, friends, comfort, is secondary. In 1911, Albert is offered a full professorship at Charles University in Prague. Better salary, more prestigious. He accepts. The family moves to Prague. Mileva hates it. She is Serbian in a city dominated by German-speaking elites and Czech nationalists. She has no friends, no intellectual community. She becomes depressed. Albert barely notices. He is working on something new, something bigger than special relativity. He wants to include gravity. Special relativity only applies to constant velocity, to inertial motion. But most motion in the universe involves acceleration, involves gravity. He needs a theory that works for all motion, general relativity. Prague is cold, grey, industrial. The apartment the university provides is adequate but cheerless. Mileva unpacks their belongings with a growing sense of dread. She knows no one here. Her German is accented, marking her as an outsider. She takes the boys to a park one afternoon, tries to make conversation with other mothers. They are polite but distant. She returns home and cries. Albert comes home late, distracted. How was your day? Fine, she says. He doesn't hear the lie. Albert's office at Charles University overlooks a courtyard filled with statuary. He spends hours at his desk staring out the window, thinking about gravity. The problem is hard. Gravity, in Newton's theory, is a force that acts instantly across space. But special relativity says nothing can travel faster than light. How can gravity be instantaneous? Albert realizes gravity must propagate at the speed of light, must be a field like electromagnetism. But what kind of field? He experiments with different approaches. Nothing works. He is stuck. In 1912, he moves again, back to Zurich, to a professorship at his alma mater, the Polytechnic. Mileva is relieved. She has friends in Zurich. The boys are in school, but Albert is barely there. He is consumed by the gravity problem. He contacts his old classmate Marcel Grossmann, now a mathematician at the Polytechnic. Grossmann knows a branch of mathematics Albert has never studied. Differential geometry, the mathematics of curved surfaces. Grossmann shows him the work of Riemann and Ricci, how to describe geometry where space itself bends. Albert sees the answer. If gravity is not a force but a curvature of space-time, if mass bends the fabric of space and time, then objects moving through that curved space-time follow curved paths. That is gravity. Not a force pulling objects together, but geometry guiding their motion. Grossmann's office is cluttered with books, journals, and papers. Albert bursts in one afternoon, breathless. "Marcel, I need your help." Grossmann looks up from his desk, amused. With what? Geometry, curved spaces. How do you describe a surface where the usual rules of Euclidean geometry don't apply? Grossmann leans back, thinking. Riemannian geometry. Tensor calculus. Why? Albert explains his idea. Gravity as curvature. Grossmann's eyes widen. That's brilliant. And mathematically terrifying. Albert grins. Can you teach me? They spend the next 2 years working together, Albert learning the mathematics, Grossmann helping him translate physical intuition into rigorous equations. It is elegant. It is radical. It is also mathematically brutal. The equations are non-linear, fiendishly complex. Albert and Grossmann work together for 2 years, developing the mathematical framework. Albert publishes preliminary papers, testing ideas, discarding failures. In 1914, he is offered a dream position, director of the Kaiser Wilhelm Institute for Physics in Berlin. No teaching duties, just research, full salary, access to the best physicists in the world. He accepts immediately. Mileva refuses to move. She has spent years following Albert from city to city, uprooting the children, living in his shadow. Berlin is the heart of the German establishment. The militarism and nationalism Albert claims to despise. She will not go. Albert goes anyway. He moves to Berlin alone in April 1914. Mileva and the boys follow reluctantly a few months later. The marriage is over. They both know it. They are living in the same apartment, but not speaking. Albert gives Mileva a written list of conditions if she wants to stay. She will prepare his meals and laundry. She will not expect intimacy or affection. She will leave his study immediately when asked. Mileva reads the list and takes the boys back to Zurich. They will not live together again. The document is typed, clinical, brutal. Mileva reads it standing in the doorway of his study. Her hands tremble. You're serious. Albert doesn't look up from his desk. If we're going to live together, there need to be clear boundaries. She feels something break inside her. Boundaries. We're married, Albert. We have children. He finally looks at her, his expression distant. This isn't working, Dolly. You know it isn't. She leaves the next morning, taking Hans, Albert, and Eduard. She does not say goodbye. She will spend the rest of her life raising their sons alone, struggling financially, bitter and heartbroken. Albert will send money when he remembers. It is not enough. In August 1914, World War I begins. Germany invades Belgium. Europe collapses into mechanized slaughter. Albert watches the German academic establishment support the war, sign manifestos endorsing German militarism. He is horrified. He signs a counter-manifesto opposing the war, calling for peace. Almost no other intellectuals join him. He is isolated. A German citizen again by technicality, living in Berlin, working for a German institution, but despising everything the war represents. He throws himself into work. For the next year, Albert barely leaves his apartment. He works on the field equations for general relativity 16 hours a day. The mathematics is overwhelming. He makes progress, then realizes he made an error, backtracks, tries again. His health deteriorates. He loses weight, suffers stomach pains, collapses from exhaustion. His cousin, Elsa Lowenthal, who lives nearby, begins checking on him, bringing him food. Elsa is warm, practical, uninterested in physics. She sees that Albert is destroying himself and tries to make him rest. He ignores her. He is so close. The equations are almost there. The apartment is chaos. Papers cover every surface. The desk, the floor, the kitchen table. Equations scrawled on napkins, on the backs of envelopes, on scraps torn from notebooks. He works in his nightshirt, unshaven, hair uncombed, smoking his pipe until the room fills with haze. He eats when Elsa forces him to, a few bites of bread, some soup. He sleeps in chairs, waking with a start when a new idea occurs to him, reaching for the nearest paper to write it down before it vanishes. He is possessed. The problem is that the equations must satisfy multiple conditions simultaneously. They must reduce to Newton's laws in the limit of weak fields and slow speeds. They must be consistent with special relativity when gravity is absent. They must be generally covariant, meaning they take the same form in all coordinate systems because physical laws should not depend on arbitrary choices of coordinates, and they must correctly describe how matter and energy curve space-time. Finding equations that do all of this is like solving a puzzle with constraints that pull in different directions. Albert tries one approach. The math works but predicts the wrong value for Mercury's precession. He tries another. This one violates energy conservation. He tries a third. It is not generally covariant. Each failure is excruciating. He can feel the answer, can almost see it, but every time he reaches for it, it slips away. He writes to friends, describes his progress, his setbacks. Some write back, encouragingly. Others suggest he is chasing an impossibility. He does not care. He will solve this or die trying. By October 1915, he is close to a breakdown. His stomach pain is constant, sharp. He can barely eat. He has lost 20 pounds. Elsa begs him to see a doctor. He refuses. Just a few more weeks, he tells her. I am almost there. She does not believe him. She has heard this before. But she brings him food, cleans his apartment when he is not looking, worries. In early November, something shifts. Albert realizes his mistake. The equations he has been working with are almost right, but not quite. He needs to modify one term, a subtle change in how the curvature tensor couples to the energy-momentum tensor. He makes the change, recalculates, checks. It works. The equations are consistent. They reduce to Newton. They predict the correct precession for Mercury. They are generally covariant. He has done it. In November 1915, he presents a series of papers to the Prussian Academy of Sciences. Each week, a new revision. He is figuring it out in public, building the theory piece by piece in front of his colleagues. On November 25, 1915, he presents the final version, the Einstein field equations, 10 interlinked differential equations describing how matter and energy curve space-time and how that curvature dictates motion. Gravity is geometry, space-time is dynamic, bending and flexing in response to mass. The equations are beautiful and terrifying. They have almost no exact solutions. but Albert finds 3. The lecture hall is packed. Physicists fill every seat, lean against the walls. Albert walks to the front, sets his notes on the lectern, and begins writing. The field equations emerge on the blackboard, line by line. The room is silent, except for the scratch of chalk. When he finishes writing, he turns to the audience. These equations describe how matter tells space-time how to curve, and how space-time tells matter how to move. Gravity is not a force, it is geometry. He waits, no one speaks. Then slowly, someone begins to clap. Others join. The applause builds. Albert allows himself a small smile. First, he recovers Newton's law of gravity as an approximation in weak fields and slow speeds. General relativity reduces to Newton when speeds are low and masses are small. This is essential. Newton's theory works brilliantly for most purposes. General relativity must include it as a special case. Second, he solves the anomaly in Mercury's orbit. Mercury, the innermost planet, has an orbit that precesses slightly faster than Newton predicts. Astronomers have known this for decades, proposed various explanations, none satisfying. General relativity predicts the exact amount of extra precession. The theory accounts for the discrepancy perfectly. Albert is ecstatic. He later says this was one of the happiest moments of his life. His theory explains something Newton's could not. Third, he predicts that light bends when passing near a massive object. Starlight grazing the sun should be deflected by the sun's gravitational field. Newton's theory also predicts light bending, but by half the amount. General relativity predicts twice the Newtonian value. This is testable. During a total solar eclipse, when stars near the sun become visible, you can measure their apparent positions and compare them to their positions at night, when the sun is elsewhere. If the positions differ by the amount general relativity predicts, the theory is confirmed. If they differ by the Newtonian amount, the theory is wrong. Everything hinges on an eclipse. World War I makes this impossible. No one is organizing astronomical expeditions in 1915. The measurements will have to wait. Albert waits. He is 45 years old. He has produced the most radical theory of space, time, and gravity ever conceived, and almost no one outside a small circle of physicists knows his name. That is about to change. The war ends in November 1918. Germany is defeated, humiliated, broken. The Kaiser abdicates. Revolution convulses Berlin. Albert stays in his apartment working on extensions to general relativity. In early 1919, British astronomer Arthur Eddington hears about the light-bending prediction. Eddington is a Quaker, a pacifist. He sees the opportunity for something larger than science. If a British expedition can confirm the theory of a German physicist, it would be a gesture of reconciliation, proof that science transcends nationalism. Eddington proposes an eclipse expedition. The Royal Society and Royal Astronomical Society agree to fund it. On May 29, 1919, a total solar eclipse will be visible from the island of Príncipe off West Africa and from Sobral in Brazil. Eddington leads the Príncipe team. Andrew Crommelin leads the Sobral team. They photograph stars near the sun during totality, measure their positions, compare them to reference plates taken at night. The measurements are delicate: atmospheric distortion, instrumental errors, plate sensitivity, all introduce uncertainty. Eddington spends months analyzing the data. Some plates are unusable, others are ambiguous, but when he averages the best measurements, the result is clear. The starlight deflection matches Einstein's prediction, not Newton's, Einstein's. Eddington sits in his study in Cambridge, surrounded by photographic plates and sheets of calculations. He has checked the numbers 3 times, 4 times. The deflection is there, unmistakable. 1.61 arc seconds. Einstein predicted 1.7. Newton would have predicted 0.87. The difference is definitive. Eddington leans back, closes his eyes, feels the weight of what he is holding. This will change everything. He writes to Einstein. The letter is brief, formal. I thought you would like to know that your theory has been confirmed. Einstein reads it in Berlin and feels a strange calm. Of course it is confirmed. He knew it would be. The mathematics demanded it. Eddington announces the results at a joint meeting of the Royal Society and Royal Astronomical Society on November 6, 1919. The hall is packed. J. Thomson, discoverer of the electron, president of the Royal Society, chairs the session. He calls it one of the greatest achievements in the history of human thought. The newspapers pick up the story. The Times of London runs the headline, Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown. The story spreads. Within days, Albert Einstein is the most famous scientist in the world. The transformation is instantaneous and bewildering. Albert wakes up unknown and goes to bed a celebrity. Journalists camp outside his apartment in Berlin. Photographers follow him to his office. Letters arrive by the hundreds, then thousands. Marriage proposals, requests for autographs, invitations to lecture in London, Paris, New York, Tokyo. People want to meet the man who overthrew Newton, who proved that time is not absolute, who bent space with equations. Albert is 40 years old. He has spent 2 decades being ignored, rejected, dismissed. Now suddenly everyone wants a piece of him. He handles it with a mixture of bemusement and calculation. He understands that fame is a tool. He can use it to promote causes he cares about: pacifism, Zionism, international cooperation. He gives interviews where he talks not just about physics, but about politics, about the need for a world government to prevent future wars. He writes op-eds. He accepts speaking invitations, traveling across Europe and beyond. Everywhere he goes, crowds gather. Not to hear the technical details of general relativity, most of them wouldn't understand that anyway, but to see him, the living symbol of human intellect. The man who looked at the universe and understood it differently. But there is a cost. Privacy vanishes. He can no longer walk down the street without being recognized. Strangers approach him in restaurants, asking for explanations of relativity, as if he can condense a decade of work into a dinner conversation. He grows weary of it. He begins avoiding public places, staying home more, seeing fewer people. The fame that was supposed to validate him, to prove that he was right all along, becomes another kind of prison. The fame is bizarre and unprecedented. Einstein becomes a celebrity on the scale of movie stars and heads of state. Photographers follow him. Journalists request interviews. Universities invite him to lecture. He receives marriage proposals from strangers. People name their children after him. Cartoons appear depicting him as a wild-haired wizard, bending space with his mind. The image crystallizes: white hair, rumpled clothes, gentle smile, the absent-minded genius. Some of it is accurate, some of it is cultivated. Albert understands the power of symbolism. He plays the part, but the fame has a darker edge. In post-war Germany, resentment festers. Einstein is Jewish. His theory is abstract, counterintuitive, difficult. It offends common sense, and it bears his name, Einstein's theory. Nationalists and anti-Semites see an opportunity. They launch a campaign against relativity, calling it Jewish physics, a fraud perpetrated to undermine German science. Philipp Lenard, a Nobel laureate physicist and ardent nationalist, leads the attack. He organizes lectures and rallies denouncing relativity and Einstein personally. In 1920, a packed auditorium in Berlin hosts an event titled The Theory of Relativity, a Mass Suggestion. Leonard and others spend hours attacking Einstein and relativity as un-German, degenerate. Albert attends the event, sits in the audience. He listens to himself being called a plagiarist, a charlatan, a Jewish corrupter of pure German science. He is shaken. He writes an angry response published in a Berlin newspaper, defending his work, calling out the anti-Semitism. His friends worry the attacks will escalate into violence. They are right to worry. In 1922, Walter Rathenau, Germany's Jewish foreign minister and a friend of Albert's, is assassinated by right-wing extremists. Albert is warned he may be next. He cancels public appearances, travels less, keeps a lower profile. The fame that made him a global icon also makes him a target. In 1921, Albert is awarded the Nobel Prize in Physics, not for relativity. The committee considers relativity too controversial, too unproven. Instead, they award the prize for his 1905 paper on the photoelectric effect. Safer, less radical. Albert does not attend the ceremony. He is in Japan on a lecture tour, trying to stay away from Berlin. The Nobel money goes to Mileva as part of their divorce settlement. They divorced in 1919 after 5 years of separation. The same year Albert's theory was confirmed. The same year he married his cousin, Elsa Löwenthal. Elsa is different from Mileva. Not an intellectual partner, no scientific training, but warm, social, comfortable managing Albert's public life. She protects him from the chaos of fame, schedules his appointments, hosts dinners. Albert retreats into his work, lets Elsa handle the world. They do not have children together. Elsa has 2 daughters from her first marriage. Albert is fond of them but distant. He has never been good with children. His own sons in Zurich rarely see him. Hans Albert, the elder, grows up resentful. His father is the world's most famous scientist, lecturing about the universe, but cannot be bothered to visit. Eduard, the younger, develops psychological problems in his teenage years, depression, then psychosis. In 1930, he is diagnosed with schizophrenia. He will spend most of his adult life in institutions. Albert writes to him occasionally, sends money. He does not visit. He tells friends he cannot bear to see his son that way. It is too painful, so he does not go. The 1920s are a strange decade for Albert. Scientifically, he is at the peak of his influence. General relativity is being tested and confirmed. In 1922, Alexander Friedman uses Einstein's equations to show that the universe cannot be static. It must be expanding or contracting. Albert dismisses this. The universe is obviously static. Everyone can see that. In 1927, Georges Lemaitre, a Belgian priest and physicist, independently derives the same result. The universe is expanding. Albert reads Lemaitre's paper and says the mathematics is correct, but the physics is abominable. He refuses to believe it. In 1929, Edwin Hubble publishes observations showing galaxies are receding from us, their light redshifted by the expansion of space. The universe is expanding, exactly as Friedman and Lemaitre predicted using Einstein's own equations. Albert travels to California, meets Hubble, examines the data. He concedes the universe is expanding. Years later, he will call the cosmological constant he added to his equations to force a static universe his biggest blunder. Though the term is complicated, the cosmological constant will eventually return in the late 1990s as dark energy, the mysterious force accelerating the universe's expansion. Einstein's blunder may not have been a blunder after all. The visit to Mount Wilson Observatory in January 1931 is humbling. Hubble, a tall man with the demeanor of a British aristocrat though he is from Missouri, guides Albert through the facility. They climb the stairs to the 100-inch telescope, the largest in the world. Hubble shows Albert the photographic plates, the spectra of distant galaxies, the unmistakable redshift. The light from these galaxies is stretched, shifted toward longer wavelengths. The farther the galaxy, the greater the shift. The pattern is consistent with an expanding universe where space itself is stretching, carrying galaxies apart. Albert studies the plates in silence. He has been resisting this conclusion for years. The universe should be eternal, unchanging, stable. That is what intuition says. That is what philosophers have believed for millennia. But the equations do not care about intuition. General relativity, his own theory, predicts that the universe must be either expanding or contracting. When he first derived this result in 1917, he thought it was a flaw. He added the cosmological constant, an extra term that acts as a kind of repulsive force, precisely to keep the universe static. Now, looking at Hubble's data, he sees he was wrong. The universe is not static. It is dynamic, evolving, growing. He should have trusted the mathematics. He should have predicted this. After examining the plates, Albert and Hubble walk outside into the cold California night. The stars are brilliant, undimmed by city lights. Albert looks up, silent. Hubble waits. Finally, Albert speaks. "I have made a great mistake." Hubble shakes his head. "No, Professor Einstein, you gave us the framework. We just had to look." Albert smiles, but there is sadness in it. The universe is larger and stranger than he imagined. More beautiful, too. An expanding cosmos, born from a singular moment. Evolving over billions of years, the implications are staggering. If the universe is expanding now, it was smaller in the past. Trace it back far enough, and you reach a moment when everything was compressed into a single point. A beginning. The Big Bang, though no one calls it that yet. The idea terrifies and exhilarates him. He has spent his life searching for eternal truths, timeless principles, but the universe itself has a history. It was born, it grows. Someday, perhaps it will die. Nothing is eternal, not even the cosmos. But the real fight in the 1920s is over quantum mechanics, the theory Einstein helped birth with his photon paper in 1905 has grown into something he despises. Niels Bohr, Werner Heisenberg, Max Born, and others develop a framework where particles do not have definite properties until measured. The electron does not have a precise position and momentum simultaneously. It exists in a superposition of states described by a probability wave. Only when you measure does the wave collapse and a definite outcome appear. Randomness is fundamental. The universe is probabilistic, not deterministic. Albert hates this. He engages Bohr in a series of debates at the Solvay conferences, gatherings of the world's leading physicists. Albert proposes thought experiments designed to show quantum mechanics is incomplete, that there must be hidden variables determining outcomes beneath the probabilities. Bohr responds to each challenge, showing how quantum mechanics remains consistent. The debates are legendary. The two greatest physicists of the era arguing about the nature of reality. Albert keeps saying God does not play dice with the universe. Bohr, exasperated, replies, "Stop telling God what to do." The 1927 Solvay conference is the most famous. The theme is electrons and photons. The conference takes place at the Metropole Hotel in Brussels, a grand building with chandeliers and marble floors. 29 of the world's leading physicists attend. The formal sessions are rigorous, polite, but the real action happens at meals and in the evenings. Albert corners Bohr after dinner, proposes a thought experiment. Imagine a box filled with radiation. You open a shutter for a precise amount of time, releasing a single photon. By weighing the box before and after, you can determine the photon's energy with arbitrary precision. By controlling the shutter, you know exactly when the photon was released. Energy and time measured simultaneously, violating Heisenberg's uncertainty principle. Bohr is silent, troubled. He doesn't have an answer. He spends the night pacing his hotel room, thinking. By breakfast, he has the counter-argument. The act of weighing the box in a gravitational field introduces uncertainty in time via general relativity. The uncertainty principle is saved. Albert listens, nods slowly. You're right. But he is not happy about it. Albert loses the argument. Quantum mechanics becomes the dominant framework. Experiments continue to confirm its predictions, but Albert never accepts it. He spends the rest of his life searching for a deeper theory, a deterministic structure underlying the quantum randomness. He is convinced it must be there. He will die convinced, and he will be wrong. Quantum mechanics is not incomplete. It is strange, but it is correct. This is one of the great ironies of Albert Einstein's life. The man who overthrew Newton by embracing radical ideas cannot bring himself to embrace the radical ideas of the next generation. In 1933, Adolf Hitler becomes Chancellor of Germany. The Nazi regime begins systematic persecution of Jews. Albert is out of the country, traveling. Friends send urgent messages, do not come back. The Nazis have raided your home, seized your property, put a price on your head. Albert never returns to Germany. He renounces his German citizenship for the second time in his life. He is 54 years old, stateless again. The Institute for Advanced Study in Princeton, New Jersey, offers him a permanent position, no teaching requirements, generous salary, a refuge. Albert accepts. In October 1933, he arrives in the United States. He will never leave. Elsa joins him. They settle into a house on Mercer Street in Princeton, a quiet college town. Albert grows his hair longer, stops wearing socks, walks to his office every day in rumpled sweaters. He is building the persona that will define him. The gentle, disheveled genius. Part of it is real. Part of it is armor. If people see him as harmless, they leave him alone. The house on Mercer Street is white, modest, 2 stories with a small porch. Inside it is cluttered. Books stacked on tables, papers covering the desk in Albert's study. A piano in the living room. Albert buys the house in 1935, the first property he has ever owned. Elsa decorates it simply. Comfortable furniture, nothing fancy. Albert's study is on the 2nd floor, a small room with a window overlooking the backyard. He spends hours there every day, working at a wooden desk that is always covered with calculations. The walls are lined with bookshelves filled with physics texts, philosophy, novels. A pipe rack sits on the desk, along with a jar of pencils and a perpetually overflowing ashtray. The 1930s and 1940s are the years of the unified field theory. Albert is trying to merge general relativity and electromagnetism into a single framework. He believes all forces must arise from geometry. Electromagnetism must be another kind of curvature in a higher dimensional space. He publishes paper after paper proposing different approaches. None of them work. Colleagues tell him it is a dead end. The strong and weak nuclear forces, discovered in the 1930s, cannot be explained by his geometric approach. Quantum mechanics is essential. Albert refuses to incorporate it. He works alone, increasingly isolated from mainstream physics. Younger physicists admire him but consider his project quixotic. They are developing quantum electrodynamics, the theory of how light and matter interact at the quantum level. It works brilliantly. Albert ignores it. In 1936, Elsa dies of heart and kidney disease. Albert mourns but does not stop working. His sister Maya moves into the house to keep him company. In 1939, war returns to Europe. Germany invades Poland. Britain and France declare war. Albert watches from Princeton, horrified. He is a pacifist, has spent years advocating for disarmament, for international cooperation. But he is also a Jew watching the Nazis conquer Europe. When Leo Szilard, a Hungarian physicist and refugee, comes to Albert in July 1939 with alarming news, Albert listens. Szilard explains that nuclear fission has been discovered. Uranium atoms can be split, releasing enormous energy. A chain reaction is possible. The Nazis know this. If they build an atomic bomb before the Allies, they will win the war. Szilard wants Albert to write a letter to President Franklin Roosevelt warning him of the danger, urging the United States to start its own atomic research. Albert is torn. He is a pacifist, but he is also a realist. The Nazis cannot be allowed to have this weapon. He signs the letter. Szilard delivers it to Roosevelt in October 1939. The letter is one of the factors that leads to the Manhattan Project. Albert is not invited to join the Manhattan Project. The US military considers him a security risk, too public, too political, too many friends in questionable places. He is kept in the dark. He spends the war years working on his unified field theory, doing consulting work for the US Navy on conventional weapons. In August 1945, he is at his summer cottage when the news breaks. Atomic bombs have been dropped on Hiroshima and Nagasaki. Hundreds of thousands dead. The war is over. Albert is devastated. He tells a journalist, "Had I known that the Germans would not succeed in producing an atomic bomb, I would never have lifted a finger." He spends the rest of his life advocating for nuclear disarmament, for international control of atomic energy, for peace. He calls the bomb the most dangerous threat to humanity, but the letter is written. The bomb exists. He cannot undo it. In 1940, Albert becomes an American citizen. He is 61. He takes the oath alongside his stepdaughter Margot and his secretary Helen Dukas. When asked if he believes in immortality, he says no. When asked what he thinks of American democracy, he says it is the best form of government yet devised. He means it. America is imperfect, but free. He can speak his mind, criticize the government, advocate for civil rights and peace without being arrested. He uses that freedom. He supports the NAACP. He testifies against McCarthyism. He calls racism America's worst disease. The FBI opens a file on him. J. Edgar Hoover considers him a subversive. The file will grow to 427 pages. In 1948, Albert is diagnosed with an abdominal aortic aneurysm, a bulge in the wall of the aorta, the body's largest artery. It could rupture at any time, causing massive internal bleeding and death. Surgeons propose an experimental operation wrapping the aorta in cellophane to reinforce it. Albert agrees. The surgery works. He has a few more years, but he knows death is close. He tells friends he is ready. He has lived long enough. In 1952, David Ben-Gurion, Prime Minister of Israel, offers Albert the presidency of Israel. It is a ceremonial role, but enormously symbolic. Albert is the most famous Jew in the world. The offer is genuine. Albert declines. He says he lacks the natural aptitude and experience to deal with people and to exercise official functions. He also says accepting would compromise his independence. He's not a politician, he is a physicist. That is all he has ever wanted to be. The 1950s are quiet. Albert continues working on the unified field theory. Every few years he publishes a new version, convinced this time he has it. Each time the equations do not work. Nature does not cooperate. His colleagues, the younger generation of physicists, stop reading his papers. They are working on quantum field theory, particle physics, the structure of the nucleus. Albert's project seems like a relic. He does not care. He is not working for recognition. He is working because he cannot stop. The universe must make sense. There must be a single principle underlying everything. He will find it, or he will die trying. His daily routine becomes ritualized. He wakes at 7, breakfast with Maya when she is well enough, though her health is failing. She suffered a stroke in 1946 and never fully recovered. She dies in 1951. Albert is devastated but silent. He does not talk about grief. He retreats further into his work. After breakfast, he walks to the Institute for Advanced Study, a 15-minute walk through Princeton's tree-lined streets. Students and professors nod respectfully as he passes. He nods back, says nothing. At the Institute, he works at his desk until lunch. His secretary, Helen Dukas, brings him tea and reminds him of appointments he will inevitably forget. Afternoons, he returns to the study at home. He works until dinner, breaks reluctantly, then returns to the desk. He fills page after page with calculations, tensor equations sprawling across the paper. Sometimes he plays the violin, Mozart or Bach, the music a kind of meditation. He plays alone, for no one. The violin is his oldest companion, the one constant from childhood. When the equations refuse to cooperate, when the mathematics leads nowhere, he plays. The structure of music, the mathematical perfection of a fugue, reminds him that order exists, that beauty is real. Visitors come occasionally. younger physicists, curious to meet the legend. They ask him about relativity, about the old days. Albert is gracious but distant. He would rather talk about the unified field theory, but they are not interested. They humor him, listen politely, then steer the conversation back to safer ground. After they leave, Albert returns to his desk. He knows they think he is wasting his time. Maybe he is, but what else is there? He has never known how to do anything but this. To stop would be to die, and he is not ready for that. Not yet. In 1955, Bertrand Russell, the British philosopher, drafts a manifesto calling for nuclear disarmament and the abolition of war. He asks Albert to sign it. Albert reads it, agrees, signs. The Russell-Einstein Manifesto is released on July 9, 1955. Albert is already dead by then, but his name is on the document. One final plea for sanity in an insane world. The manifesto calls on scientists to remember their responsibility to humanity. Knowledge is not neutral, weapons are not inevitable. Choose life, not death. The message is simple, the world ignores it. On April 13, 1955, Albert collapses at home on Mercer Street. The aneurysm is leaking. He is taken to Princeton Hospital. The surgeons tell him they can operate, try to repair the rupture. He refuses. He asks for his most recent calculations to be brought to the hospital. He wants to work. On the night of April 17th, he revises a draft of a speech he was supposed to give for the 7th anniversary of Israeli independence. He writes about the dangers of nationalism, the need for international cooperation. He never finishes. Around 1 in the morning on April 18th, the aneurysm ruptures completely. Internal bleeding, shock. He dies at 1:15 a.m. His last words are in German. The night nurse does not speak German. We do not know what he said. The hospital pathologist Thomas Harvey removes Einstein's brain during the autopsy. He does not ask permission. He weighs it, photographs it, dissects it into 240 pieces. He keeps the pieces for decades, claiming he is studying them, looking for the anatomical basis of genius. He finds nothing. Some studies claim Einstein's parietal lobes are slightly larger than average, possibly explaining his spatial reasoning. Other studies dispute this. The truth is, the brain shows nothing extraordinary. It is a normal human brain. The genius was not in the tissue, it was in how the tissue was used. Albert Einstein's ashes are scattered in an undisclosed location. No grave, no monument, just the equations, the papers, the legacy. Within hours of his death, newspapers around the world run obituaries. The greatest scientist since Newton is gone. The man who showed us the universe is stranger and more beautiful than we imagined. The man who proved that time is not absolute, that space can bend, that matter and energy are the same thing. The man whose theories made GPS satellites possible, explained the orbits of planets, predicted black holes and gravitational waves and the expanding universe. The man whose face is instantly recognizable to billions of people, most of whom could not explain relativity if their lives depended on it. That man is dead, but the story is not about the theories. The theories are important, revolutionary, foundational, but they are not the point. The point is how he got there. The point is that every institution designed to recognize and cultivate genius rejected him. The point is that the patent office, the dead-end job, the years of obscurity, were not obstacles. They were the conditions that made everything possible. If the Swiss Polytechnic had given him an assistantship in 1900, he would have become a competent academic physicist, contributing modestly to the field, publishing safe papers, earning tenure. He would not have overturned Newton. He would have been too busy doing what he was told. The rejection forced him to think independently. The isolation freed him from intellectual fashion. The patent office gave him just enough money to survive and just enough time to think. And the problems he worked on, the questions that obsessed him, were not the problems everyone else was working on. They were the problems that made no sense, the contradictions no one else wanted to touch. What happens if you chase a beam of light? How can light be both a wave and a particle? How can the laws of physics be the same for everyone if motion is relative? These are not the questions of someone trying to get published or impress a professor. These are the questions of someone who needs to understand, who cannot function without understanding, who will rip reality apart and reassemble it till it makes sense. That desperation, that need, is what created the miracle year. Not genius in the abstract, not IQ points or raw computational power. Genius as a response to exclusion. Genius as the thing you do when no one is watching, when no one cares, when there is no reward except the answer itself. Einstein succeeded because he was unwanted. The world said, "You do not belong here." And he said, "Fine, I will build my own world." The unified field theory failed. 30 years of work, hundreds of pages of calculations, a dozen different approaches, and none of them worked. The theory he thought would crown his career, the final synthesis, the equation to end all equations, does not exist. Or if it exists, he could not find it. He died, still searching. Some see this as tragic. The great mind, dulled by age, chasing a ghost. But there is another way to see it. He never stopped. The world moved on. Quantum mechanics became orthodoxy. His colleagues told him to give up. He kept going because stopping would mean accepting that the universe is random, that God does play dice, that there is no final answer. He could not accept that. So he kept working, even when it was hopeless, even when he knew it was hopeless, because the work itself was the point. His personal life is harder to defend. He abandoned his daughter. He neglected his sons. He treated his first wife as a servant. He was a terrible father, a worse husband, and he knew it. He wrote letters to Hans Albert late in life, admitting he had failed as a father, saying he wished he had done better. But he did not do better. He chose physics over family every time. Some biographers try to soften this. They emphasize his warmth with friends, his playful humor, his violin playing. All true, but also irrelevant. The people who needed him most, his children, got almost nothing. That is the cost of genius, or the cost of selfishness, or both. It does not matter what you call it. The cost was paid by people who did not choose to pay it, and yet what he gave the world is incalculable. Before Einstein, space was an empty stage, time was a universal clock, and gravity was a mysterious force acting across the void. After Einstein, space and time are a unified dynamic fabric. Gravity is geometry, and the universe is a four-dimensional structure bending and stretching according to equations we can write down. Before Einstein, matter and energy were separate substances. After Einstein, they are two forms of the same thing, interchangeable, bound by the most famous equation in physics. Before Einstein, the universe was assumed to be eternal and unchanging. After Einstein, we know it is expanding, it has a history, it had a beginning. Every time a GPS satellite corrects for time dilation to give you accurate directions, that is Einstein. Every time astronomers detect gravitational waves from colliding black holes, that is Einstein. Every time a nuclear reactor converts mass into energy, that is Einstein. Every time a physicist explores the edge of a black hole or models the Big Bang or tries to reconcile gravity with quantum mechanics, they are working within the framework Einstein built. The language of modern physics is the language Einstein created. Even the parts he disagreed with, even quantum mechanics, grew out of ideas he initiated. But beyond the equations, beyond the technologies, there is something else. Einstein changed what it means to think about the universe. He showed that common sense is not reliable, that intuition fails, that the universe does not care, whether its rules make sense to human brains evolved to throw spears and avoid predators. Relativity is counterintuitive. Time dilation feels wrong. Length contraction feels absurd. And yet it is true. Reality is stranger than we are built to comprehend. The only way to understand it is to follow the math. Even when the math leads somewhere uncomfortable, trust the equations, not your gut. That is Einstein's deeper legacy, not the specific theories, but the method, the willingness to abandon everything you thought you knew if the evidence demands it. And the man himself, the wild-haired icon, became something more than a scientist. He became the symbol of human intelligence, of the capacity of the mind to unlock nature's secrets. When people say Einstein, they do not mean an individual. They mean the possibility that one person working alone, armed with nothing but thought, can change everything. It is mythology. It is not entirely accurate. Einstein did not work alone. He built on Maxwell and Lorentz and Poincaré and Minkowski. He collaborated with Grossman, debated with Bohr, learned from Planck. Science is collective, cumulative, built by communities over generations. But the mythology persists because people need it. They need to believe that the individual matters, that genius is real, that one mind can make a difference. Einstein did make a difference, but not because he was a solitary genius untouched by the world. He made a difference because he was shaped by rejection, driven by obsession, freed by failure. The patent office years were not a detour. They were the crucible. The outsider status was not a tragedy. It was the precondition. He rewrote the universe because no one told him he was not allowed to. And the questions he could not answer, the unified field theory, the interpretation of quantum mechanics, those failures matter too. They remind us that even the greatest minds hit walls, that some problems are harder than one lifetime, that the universe does not owe us answers just because we ask. Einstein spent 30 years on the unified field theory and got nowhere. But in trying, he kept the question alive. He showed that it is worth asking, even if you cannot answer it. Future physicists will attempt what he could not. Maybe they will succeed. Maybe the problem is unsolvable. Either way, he pointed the direction. April 18th, 1955. The brain in the jars, the ashes scattered in secret, the equations that will outlive the species that wrote them. Albert Einstein is gone, but the curvature of space-time remains. The photons still carry quantized energy. The universe still expands. Oblivious to whether anyone is watching, he showed us how to see it. That is enough. That is everything. The man who failed to get an academic job because his professors thought he was arrogant. The man who worked in a patent office because no university would take him. The man who wrote the most revolutionary papers in physics while completely outside the system. That man changed how we understand reality, not by conforming, not by following the rules, but by being rejected so thoroughly that he had no choice but to build something new. That is the story, not genius bestowed by birth, not divine inspiration, just a stubborn man who refused to stop asking why, who could not accept answers that did not satisfy him, who kept thinking even when thinking led nowhere, who believed the universe made sense even when it looked insane. And because he believed it, because he kept looking, he found things no one else had seen. He bent space and time with nothing but thought. He showed us that reality is stranger and more beautiful than we imagined. He proved that one person, armed with curiosity and stubbornness, can change everything. Albert Einstein died believing he had failed. The unified field theory was incomplete. The quantum problem unsolved, but he was wrong about failure. He succeeded in ways he never intended. He became the symbol of what the human mind can achieve when it refuses to accept limitations, when it looks at the universe and says, "I do not understand yet, but I will." He never finished. But finishing was never the point. The point was the search, the endless, exhausting, exhilarating search for truth. That search does not end. It continues in every physicist working today, every student learning relativity, every person who looks at the night sky and wonders how it works. The search is Einstein's true legacy, not the answers. The question, always the question. What is the universe really? And how can we know? He spent his life asking. The question remains. That is enough. That is everything.